Alright guys, we're going to try this using the PowerPoint this time. This is Unit 1, Lesson 5, Parent Functions and Transformations. We've analyzed graphs over the last few lessons. We've looked at end behavior limits, extrema, etc. Today we're going to start pulling it all together, and we're going to start talking about using those things with parent functions, and we're going to do graph transformations of parent functions. So new vocabulary: parent function, constant function, zero function, identity function, quadratic function, cubic function, square root function, reciprocal function, absolute value, step function, Grace integer function, transformation, translation, reflection, and dilation. All of these you have seen in the past in Algebra 2. We're going to start with a constant function. Constant function is just f of x equals some number c. They are horizontal lines. The identity function. The identity function is going to be a straight line that looks like it's the 45-degree angle. It's f of x equals x, or y equals x. The quadratic function, f of x equals x squared, has a u-shaped graph. This is the parabola. This is our u-shaped graph. You'll notice that this has reflection, the parent graph of this has symmetry over the y-axis, which makes this an even function. Cubic functions, f of x equals x cubed, is symmetric around the origin. With this being symmetric around the origin, we see that this is an odd graph. With this I want you to remember this cubic function. This is the function that I said was the John Travolta graph. We're going to start calling it the cubic function rather than saying it's the John Travolta graph, though. Square root and reciprocal parent functions. The square root function, it looks like half of a parabola on its side. It's f of x equals square root of x. The reciprocal function, also a hyperbolic function, has the form of f of x equals 1 over x. This has two asymptotes. The y-axis is one of the asymptotes. The x-axis is the other asymptote. I want you to recall that asymptotes are imaginary lines on the graph that the blue line, or the graph itself, the function itself, will get extremely close to it, but it will never touch it or cross it. This is the absolute value function. The absolute value function looks like the v function. The Grace integer function. This is kind of a difficult one for a lot of people to understand. This is what it looks like. It looks like two lines with an x in there. Not to be confused with the absolute value function. We are looking at, it is defined as the Grace integer less than or equal to x. So if I look at negative 4, what's less than or equal to negative 4? Well, negative 4. I'm looking for an integer that is less than or equal to negative 1.5. Well, the next lowest integer is negative 2. I'm looking for an integer that is less than or equal to 1/3. Well, the next one lower than that is 0. When we graph this, you'll notice that this kind of looks like a stairs going up. This is also known as the step function. Describe the following characteristics of the graph of the parent function f of x equals 1 over x. They want the domain, range, intercepts, symmetry, continuity, end behavior, and intervals on which the graph is increasing and decreasing. So, first thing I do is I graph the function. I want to see what it looks like. So I pull up a graph of this. And now I'm going to list the domain. The domain of this function, the domain are all the possible x values. When I look at this is previous lessons, so I'm going to go right through this. The domain of this function, negative infinity to infinity. The range is a little, I'm sorry, that is not, the domain is not that. The domain of this is negative infinity to 0, and then union 0 to infinity. The range is going to be the same thing because there's asymptotes in this. So it's negative infinity to 0, union 0 to infinity. Notice that this has parentheses on it because it can't be 0. Okay, so that's just the domain and the range. The continuity of this. When I'm looking at this graph, I can see that there's going to be discontinuity. In fact, this is the where the graph keeps going on toward infinity in both directions. So this has the infinite discontinuity. So we've got infinite discontinuity. Next, they also wanted intercepts and symmetry. So when I'm looking at this, this has no intercepts because it does not intersect the x and y axes. So no intercepts. Also, this has symmetry, and if we took and rotated this graph that way, we would see that it would land on top of each other. So it's rotating about the origin. So this has this is symmetric about the origin. And if it's symmetric about the origin, we know this is an odd graph. We also needed end behavior and intervals of increasing and decreasing. So if I'm looking at end behavior, we're going to use limit notation. So we're going to say the limit of this 1 over x as x goes toward negative infinity is going to be 0. Also, the limit of this function 1 over x as x goes toward infinity is also going to be 0. Now, when I look at this function, I can tell that this is decreasing all the time. So this is decreasing from negative infinity to infinity. These are the things you're going to have to put on your homework. It's going to be asking for all of these things. You're going to have to know what that infinite discontinuity, the jump discontinuity, if it's continuous all the way. So now, this says describe the following characteristics of the graph of the parent function f of x equals x squared. Domain, range, intercepts, symmetry, continuity, end behavior, etc. So I'm just going to head back to our parent functions, because that was a nice graph. Here's the quadratic x squared. This is the parent function. When I look at this, I can automatically see that my domain is going to be from negative infinity to infinity. The range is going to be from 0, because that's our lowest y value, to infinity. This is going to be a continuous function. There is no discontinuity in this function. The symmetry is about the y-axis, so I would say this is symmetric about the y-axis, therefore this is an even function. This has an intercept, an x-intercept of 0, and a y-intercept of 0, because it crosses the x and y-axes at 0, 0. The end behavior of this is as the limit of x squared as x goes toward negative infinity. It keeps going up, so it must go toward infinity. The limit as x squared goes toward positive infinity is going to be also positive infinity. This graph is decreasing from negative infinity to 0, and it's increasing from 0 to infinity. If you are struggling with any of these concepts, my advice is to go back and watch the videos from the previous lessons. We're going to talk about vertical translations and horizontal translations. This should sound very familiar from Algebra 2. G of x equals f of x plus k. K is our vertical translation. If k is positive, it moves up. If k is negative, it goes down. Horizontal translations. This is the one that was a little awkward for us. Whatever h is, we do the opposite of. If h is positive, we go backward. If h is negative, we go forward. So this is where our h is negative. We have x minus h. We moved in the positive direction. This is where x is x plus h. We moved in the negative direction. So use the graph of f of x equals x cubed to graph the function g of x equals x cubed minus 2. So we start with our parent function, f of x. G of x, we see that we have a minus 2. This tells me that k is minus 2. So I'm going to take my parent function. You always start with your parent function. You start with your parent function and you move it down 2. So I would take this and it would go down 2. This point right here would go down 2. This point right here goes down 2. So once we move all these points down 2, we would connect them in a nice smooth line, and we get this. Use the parent graph of f of x equals x cubed to graph the function g of x. If g of x is x minus 3 cubed. Again, we start with our parent function. This time we have this minus 1. So this means I'm going to move in. This is our h. Notice that we have a minus h. Therefore, we move in the positive direction. We're going to move all of these points over 1 unit. Okay, and then we plot all those points coming in a nice curve, and we get this answer. H and K. H moves left and right, K moves up and down. Now we've got two going together at the same time. Again, we start with our parent graph. We always start with our parent graph. Please do not make any graphs with translations that do not have your parent graph on it. This moves it to the right 1 unit and down 2 units. So you're going to move right 1, down 2. Take this point right here. Right 1, down 2. This point right here. Right 1, down 2. When you connect them, you have a nice smooth curve. There's your final answer. Go ahead and push pause. I will give you 10 seconds to answer this question. Hopefully you came up with the answer of B. Reflections in the coordinate axes. When we have a reflection, the whole function is negative. We reflect it in the x-axis. If just the x portion is negative, we reflect it in the y-axis. Remember that, please. So when I'm looking at this describe how the graphs of f of x, which equals square root of x, and g of x are related. Then write an equation for g of x. So first of all, they're related because they're both the square root of x. What we see is g of x has been moved up 1 unit. So that means we have an additional k. So we would start with g of x, and that equals the square root of x. K moved up 1, so we're going to say plus 1. There's our answer. All done. That simple. Now this time we see that f of x, still a square root function, but this time it's been moved back 1 and then it's been flipped over. So, and it's been flipped over the x-axis, so the whole function has to be negative. So I start with g of x, and that's going to equal the square root of x, and it moved back 1, so that's my h. So I'm going to say plus 1, and then the whole thing has to be negative, so I'm going to put a negative out in the very front. Vertical and horizontal dilations. Vertical dilations, if there's an a out in front of the whole entire function, then it's a vertical stretch or vertical compress. And what you do is you take the whole entire function, or your y values, and you're going to multiply them by whatever your dilation factor is. With the horizontal dilations, you take your x values and multiply them by the reciprocal of your dilation factor. Remember that. The reciprocal of your dilation factor. Identify the parent function. So f of x, our parent function is going to be the reciprocal function, which is 1 over x. Describe how the graphs of g of x and f of x are related. They're both from the reciprocal family. Then graph f of x and g of x on the same axes. So if I'm going to graph these, so now I'm looking at this and I'm going to say, well, they're both reciprocal, so I start with the parent function. Now the parent function, we've seen the parent function up above. This isn't a perfect graph. Obviously, I'm trying to do this on a tablet, but this is our parent function. When I look at this parent function, I'm going to take each one of these points and I take the y value and multiply it by 3. So this point this is supposed to be 1, 1. I multiply the y coordinate, which is 1, by 3, and it moves it up from 1 to 3. So it's now up there. So I've got this new point that's 1, 3. This point that's right here at -1 is going to be now -1, -3. So you get this new graph. See the 1 multiplied it by 3, you are now here. This 1/2, or I'm sorry, at x equals 2, my y coordinate's 1/2. I multiply 1/2 by 3, and I get 1 and 1/2. Now this time I have this 4, but this 4 is inside with the x. It's not out front. It's inside with the x. When it's inside with the x, that means you multiply your x coordinates by the reciprocal of 4. The reciprocal of 4 is 1/4. It's 1/4. So I multiply each one of my x coordinates by 1/4. So if I take my x coordinate right here, that would be 1. Multiply that by 1/4, and I'm now right here. Take your x coordinate that's at 2, multiply it by 1/4, and I'm now at 1/2. Take this x coordinate that's at 4, multiply it by 1/4, and that puts me at 1. Same thing over here. Now, because this function was negative, it has to flip over, and the negative's out front, this has to flip over the x-axis. So I would connect these in a nice straight lines. Yeah, straight lines. And then reflect it over, and I get this final blue graph. It's much harder to draw on the tablet with a PowerPoint than the other program I was using. Much harder. Alright, so identify the parent function of this. This we can tell is going to be the cubic graph. Now the 0.5 is inside with the x. So I multiply each one of my x values by 0.5. This is a negative, so it has to flip over the x-axis. So let's try to graph this again. Obviously, I'm trying. So now, this is the cubic graph. So, the cubic graph does this. Okay, and now each one of these x values gets multiplied by gets multiplied by the reciprocal of 1/2, which is 2. You multiply by the reciprocal of 1/2, which is 2. So this point that's at 1, 1, I multiply the x coordinate by 2, that puts me at 2. I multiply the 2 by 2, the x coordinate of 2 by 2, and that puts me at 4. Now, the negative is going to flip this around, so my final graph would be a very stretched out cubic. If you need help in class with this, this is probably the toughest concept of this lesson. So when I'm looking at this, I look and I say, okay, so it has to be stretched out and flipped around. Note this is stretched out, but it's not flipped over the x-axis. This is flipped over the x-axis, but not stretched out. This is a parabola starting as my f of x, and that's not right. So it's b, and it has to be. Now we're going to start with piecewise functions. Remember, piecewise functions are those functions that are pieces of functions. So when I'm looking at f of x, looking at this whole giant piecewise function, when x is less than 0, I have to use this function. When x is between 0 and 2, I have to use this function. When x is greater than 2, I have to use this function. Now, the easiest way to do this, guys, is to plot points. So, again, I'm going to start with a graph. I'm going to be a good graph. Yes, and now I can count. Alright, so x is less than 0. So let's choose 0. Well, let's choose values less than 0 and plug them into this function. Because we know when x is 0, we have to be with this function. So we're going to say -1. -1, we plug it in, we get -1 plus 2. That's 1. Absolute value of 1 is 1. So we've got a point here. I plug in 0. I plug in -2 and I get 0. I plug in -3, I'm back at 1. I plug in -4 and I'm at 2. And it's going to continue going in that direction. Okay. Now, I can go up to 0 though. I just can't be 0 and use this function. So if I plugged in 0, I would be at 2, but since I can't be at equal to with this function, I have to put an open circle. Open circle, no equal to sign means open circle. From 0 to 2, I have to use this function, where that's, well, I'm going to choose 0 and plug it in. 0 minus 2, so that puts me at -2, so I've got a point here. Okay, so now I'm going to choose 1. I choose 1, I plug in a value, 1 minus 2, that puts me at -1. Choose 2, that puts me at 0. Now from 0 to 2, those are going to be closed circles, so I better make sure those are closed, and then I connect those. Now for things greater than 2, I have to use this function. Again, just choosing points. This can go up to 2, but it cannot be equal to 2. So I'm going to start by choosing 2. 2 minus 2 is 0. Square root of 0 plus 2 is 2. So at 2, I have an open circle. Square root, and then I'm going to plug in 3. 3 minus 2, 1. Square root of 1 is 1. Plus 2 is 3. So at 3, I'm at 3. At 4, I am at a little above 2. Not a lot. And since it's a square root, we see that it's going to go off like that. Here's our piecewise functions. Here's the first piece, here's the second piece, here's the third piece. You will notice that this passes the vertical line test. If you get done graphing your function and it doesn't pass the vertical line test, you did something wrong. And this is the final answer. This is probably much better looking than what I had. So looking at this, when x is less than -1, we have to use this function. So this is a square. This is a parabola. So let's see. All those first functions are parabolas. But we know that we have to have an open circle. So that one's gone. Now between -1 and 2, I'm going to have closed circles. And this is also part of a parabola. So looking at this, let's see, that has closed circles. Oh, no, not this one. And this one has closed circles. Good. So now we have to look at this one. This is a square root function. And the square root function for those has to have open circles. They both have open circles. So now we have A and D to choose from. So this is what I would do with this, is I would say, let me plug in 2. 2 minus 2 is 0. Square root of 0 is 0. So at 2, I would be at 0, which is this one right here. So your answer would be A. Because this one is not on 0. It is way up here at 4. So that can't be it. Transformations with absolute value. Absolute value, if the whole thing is being absolute value, we take whatever's on the underneath and it gets flipped up over the x-axis like this. If just the x portion is being absolute value, we eliminate this portion and then reflect whatever is over here onto this side over here. So we can see that use this graph to graph the function. They want the whole thing being absolute value, so that means this portion down here gets flipped up there. This time they just want the x portion, so we eliminate this and then reflect the whole thing over. Graph this, assuming that you're going to graph g of x, where the whole thing is going to be absolute value, and then you're going to graph f of h of x, which just the x portion is absolute value. So with the whole thing, we just take whatever's negative and it gets flipped up. So this portion comes up to the top and goes up like that. With the h of x, we eliminate half and then flip it over. So we eliminate the bottom halves. So let's see, is this, we're looking for g of x. Here's the g of x that we talked about. Is this the h of x? No. Here's the g of x we talked about. Is this the h of x? Yes. So our answer would be B. And that's at the end of this lesson. Hopefully you can get through your homework and what you need to with this.